Good morning. This is Pietro Calandra, and I wanted to first of all to thank the organizing committee for giving me the opportunity to stay here and to show you what I'm doing in my research. As you can see from the title, I will show you some nice properties of ionic liquids and to show you how computational chemistry can help. Computational chemistry made by a cheap computer, so an approach that definitely everyone can reach. A few words about me. I am a senior researcher at the National Council of Research in Italy. This is the place where we work. As you can see, it is very green, clean, silent, quiet place, a perfect place where to work. In my outline, I will follow this scheme. First of all, I will show the systems, the properties, the approach we suggest, and the solution. So the topic is chemistry of materials. In this field, the chemists want to prepare ad hoc materials, new materials with desired properties. There are a few strategies that are very well known. The first one is the preparation of new molecules. This is typical of synthetic chemistry. You prepare a new molecule, like a new polymer, and you end up with plastics, so a new material. Then there is another structure that is the preparation of nanostructures. Basically, you reduce the size of a sample of a given material and you end up with new properties. For instance, you can have gold of different colors according to the size of particles. Usually in the nano state, many properties change, so you can tune the properties with the size of the piece of materials, basically. A third strategy is the preparation of composites. So you blend two different materials, and the union of these two materials, give a new property. This is quite a nice strategy because usually it's hard to foresee the new property that will arise when you mix two materials. This is quite unpredictable, so there is a link with the imagination in science. In any case, we prepared ionic liquids with a novel system, with a novel strategy. In the past, ionic liquids, that is a very interesting field of material chemistry, they are made by salts that are liquid at the room temperature. Salt like the salt we use in the kitchen for cooking, so it's made of ions, and they have a crystalline structure. They are solids. In the case of ionic liquids, you have the same kind of materials, but the state is liquid at room temperature. It's like a salt that is molten, but a very low temperature. At room temperature, it is already melt. And they are very interesting because you have the ionic nature of the materials, but you have the liquid and the mobility structures. In the past, there have been many efforts to prepare new ionic liquids by synthetic chemistry. So there are many protocols, very expensive, very polluting strategies to prepare ionic liquids, very complicated. But we found a very cheap and easy, straightforward way that is based on the blending of two materials. You have one component, usually a basic material. You have another liquid, an acidic one. If you mix them, the acid gives the proton to the basic species, so you end up with a cation and an anion. I pointed that in the opposite way. The deprotonated acid is the anion, and the protonated species is the cation. So these two ions are still the liquid states, so you end up with the ionic liquid. Very straightforward, very easy. In addition, given the particular structure of these two molecules, you end up with also other contribution to the total structure, so you end up with new properties together with the ionic liquid itself. This is the scheme. When you have a simple liquid, there is no structure. When you have one component made by an apolar part and an apolar part inside the same molecular structure, you have some structuring. But if you mix two surfactants, so for instance, this guy with this other guy, for chemists, the green is the phosphorus atoms, these are oxygens, and these are apolar parts. This polar part wants to interact with the polar part of the other molecule. So you have a complex pattern due to the fact that each molecule has a polar and an apolar part, but you have another contribution to the total complexity due to the fact that you have two components. So you have this apolar part that wants to interact with itself and with the other guy. The property that emerge when you have this mixture can be striking. I will show you what happens when you mix two liquids. The volume is not the sum of the two contributing volumes, but there is another contribution due to the fact that the emerging volume is rising. So the volume basically is not additive, but this equation is valid for the volume, but also for molar refraction, for the density, for conductivity. In this scheme, I am plotting the conductivity as a function of composition. These substances here has this conductivity. This is pretty insulating, but when you mix them, the trend is made by the experimental red points. And mind that this is a logarithmic scale, so the increase is of several orders of magnitudes. Things are even more striking when you mix this guy that is pretty insulating with this other one. This is caprylic acid, it's a natural acid found in milk. They are pretty insulating, but if you mix them, the conductivity increases of about 9 orders of magnitudes. So the properties of these ionic liquids are strikingly. So this is the point. You need two different species, one acid and one basic. We focused our attention to alkyl phosphates as acidic species and to alkylamine as basic ones. So you can have different molecules for alkyl phosphates, the acids, and you have different molecules for alkylamines, the basic ones. You can mix these with this one with the second one, this one with the third one, so you have all the possible combinations. So 3 times 3 possible combinations. The computational chemistry is nowadays based by the density functional theory approach with an ensemble of functions that can be quite reduced in our case, and closed shell means that there are no electrons, the electrons are coupled, let's say. In any case, in this framework, let's study what happens if you mix this molecule with this one and all the other combinations. So you have a total number of nine systems. This couple, this one, and the other ones. This is the strategy. You have a general problem, but you can divide the big problem into sub problems. So you can explore first first of all the first couple, the second couple. You have 9 couples. If for each of them you have different chemical species. Then for each chemical species you have 1 conformer, 2 conformers, 3 conformers. You have many conformers because the molecule can find different conformations, so you can study by ab initio the energetics of each of them. Basically, what a very big computer can do can be made by many trash computers. The difference is that this is very expensive and these are for free. You can find them, actually I found them for free in social groups. So if you parallelize the problem into many sub problems, you can use different PC, each of them dealing with a single task. The basis set is quite reduced, so you focus on the very essential part of the chemistry problem. You can increase the speed of the old PC by buying this adapter. Instead of putting the GPU for graphics, you use the same slot, PCI Express slot, to insert a solid state device for saving data. So this costs a few euros, and now the NVMe SSD costs very little. In this framework, you can use your old PCs to do what workstation can do, even if you have to wait a bit longer. But the chemistry problem is very simple. You are just studying a couple of molecules. You are not studying a system made by hundreds, thousands of molecules. So the key point is that you can update with no cost very old PCs found for free. And on the other side, they are able to study particular aspects that computational chemistry made by very expensive workstation has not yet investigated. So this gap of knowledge can be filled by the use of old PC. And this is the take-home message. Find a topic which has not studied yet. If the topic is simple to manage, you can use your old PC. So in this case, there is a match between hardware, cheap hardware, and the capability of finding the aspects of your chemistry problem that can be faced in a simple way. And these are the results. Usually in this case, where the phosphate has phenyl rings, there is a proton exchange from one species to the other one, so you end up with an anion and a cation, but there is the electrostatic stabilization, so you end up with the total structure. Mind that here the proton is lost. This proton is not in this species, but is in this species, and they are still in liquid states. Of course, there are also experimental proofs that the system is still liquids. In this other case, the same happens. You have this guy here giving the proton, you end up with cation and anion, they interact, so they are still in the liquid states, and you can work out all these contributions by working out these energetics, the energy of each single species. As a scheme, we can say that a guy gives the proton, but this process is not spontaneous because it requires energies. But then the stabilization of these two species, making a compact complex, stabilize the overall energy. So the overall process is spontaneous. By ab initio calculations, we found that there is a direct hop from this state to the other one. So this is just a scheme to understand all the contributions involved, but in reality, this mechanism is, we say, concerted. So they are not separate in time, but they happen all together, simultaneously. So the proton hop and the stabilization are synchronous. So the system is not experiencing activation energies in this case, but there is a direct transition from the two isolated species to the complex, final complex. What is interesting is that also the pure components are interacting. This guy is interacting with itself. This acidic one is interacting with itself. But the energy is, this stabilization energy is quite low. Instead, if one guy is interacting with the other counterpart, the stabilization energy is much higher. The proton here, you see, the proton is attached to this molecule and the same as in this. But here, the proton hops to the other one, making two ionic species very strongly interacting. So the energetics gives you the answers. So, thanking you, I want to recall that we found very easy systems to explore, to understand what happens when you mix one acidic one alkyl phosphate to an alkylamine together, and given this gap of knowledge that can be faced in a simple way, very cheap computers can be ready for this. So I thank you for your attention.